All right. So just a reminder that our test is on Wednesday. And hopefully the idea is we're going to try to cover everything that's going to be on the test today, basically. That's the plan. I know we are a little ahead of schedule in the PowerPoints. Like the material I asked you to watch and do the reading guide for today, I introduced that on Wednesday. And some of the stuff we're going to go over today isn't introduced until Monday. But what that'll allow us to do is, since we're a little ahead of schedule, we should have some time on Monday to do some review. So what I asked for you, though, is that this is going to be student-led review, in that you bring me any questions that you want for the second half of Monday once we finish up the lecture, and I will answer those. So if you have problems you want to go over, homework problems you want to go over, any general questions, have those ready to go, and I will cover them on Monday for our test on Wednesday. All right, so what we were talking about on Wednesday is that we were looking at light and energy, and we talked about the visible spectrum of light a little bit. We talked about how elements can emit energy and how elements can absorb energy, and the energy that they emit and that they absorb are the same wavelengths. Then we ended at looking at this equation by Rydberg, which is an equation that shows us for the hydrogen atom, what wavelengths of light can we expect to be emitted, and what wavelengths of light can be absorbed. And this equation is based on energy levels. So the M and N variable here are energy levels. Just think of energy levels as different positions or different states electrons can take. We'll get more into energy levels actually later today. But Rydberg didn't really know like how atoms behaved. He couldn't really explain why this happened, but his equation shows that, you hit a hydrogen with some energy, we can expect some to be absorbed and some to be emitted. So what we're just going to do in their first equation is use Rydberg's equation, or our first question is use Rydberg's equation and try and calculate the light emitted when an electron makes these energy transitions. So these different energy levels are just levels electrons can be at. And so I'll do A for us to actually show you what's going on. All right, so we have an electron. And initially, the electron is at an energy level of 1. That's what this N equals 1. We hit this electron with energy and make it go to the N equals 2, or second energy level. First energy level, second energy level. And what we want to figure out is what type of light do we need to shine at this electron to make that happen? Because electrons, they absorb discrete amount of energy. So discrete. Do not know if I spelled that correctly, but close enough. So what it means is that electrons only absorb like one wavelength. They don't absorb all light. They only absorb one wavelength. So what we want to calculate using this equation is how much energy do I need to absorb to go from the first energy level to the second energy level? And that's where Rydberg's equation comes in, right? So Rydberg's equation is 1 over the wavelength of light. Remember that lambda, this Greek lambda means wavelength of light, equals Rydberg's constant, R, which is a given. Do not confuse this with the gas constant. This is completely different, even though they're both R, multiplied by 1 over m squared, which is the energy level we start with, minus 1 over n squared, which is the energy level that we end with. So let's plug in our variables. So 1 over wavelength. We're solving for wavelength, so we don't know what that is. That's what we're solving for. Equals Rydberg's constant, 1.098 times 10 to the 7 meters, multiplied by 1 divided by our initial energy state squared. Our initial is 1, so it's 1 squared, minus our final energy state, 1 divided by 2 squared, right? And so when you plug all that in, you'll get 1 over wavelength equals 8235000. So 8,235,000. This is an inverse wavelength. This is 1 divided by wavelength equals this number. We don't want 1 divided by wavelength. We want actual wavelength. So when you come to this part of the problem, or any problem where you have 1 divided by variable equals a number, to get the variable by itself, you take your large number and you do 1 divided by this number equals wavelength. So if you do 1 divided by 8,235,000 on your calculator, you should get the wavelength. And you get wavelength equals 1.21 times 10 to the minus 7 meters, or 121 nanometers, which is UV light. So there's a couple. One, you don't have to put it in nanometers if you don't want to. I just did that conversion for us. You can leave it as 1.21 times 10 to the minus 7. But how do you figure out where that is? How do I know that's in UV light? Well, we go down to our spectrum. We find out that we're 10 times, whoops, that was kind of, didn't do a good circle there. We find out where 10 times raised to the power minus 7 is. Draw like a little arrow, and we see that's UV light. So for an electron to be promoted from the first energy level to the second energy level in hydrogen, we need to shoot UV light at it with a wavelength of 121 nanometers. It will only absorb energy at that wavelength. Any question about that calculation or what this calculation is trying to show, any of the logic or anything to do with this problem? You're getting a number. So if you're getting another number, what might be happening, I'll just double check my work, is that if you're trying to plug this all into the calculator at once, it's possible it's possible the order of operations is not doing what you think it's doing. Yeah, because I just did it really quickly and I got the same answer again. So make sure you're using parentheses or do it parts at a time in your calculator, because if you throw this all in the calculator at once without using parentheses, it's possible that this will throw up the wrong answer. So that's why I'm a big proponent of doing calculations piece by piece and writing down the answer. But if there's no other questions, try and do B. See if you can follow what I did for A and tell me what wavelength of light I need to absorb to go to the energy level 1 to energy level 3. Right, let's see if we can follow the same type of logic for B, right? So it's the same equation. Get my pen back up. 1 divided by wavelength equals Rydberg. So Rydberg is 1.098 times 10 to the minus, 10 to the 7, not minus 7, multiplied by 1 divided by initial energy level squared, so 1 divided by 1 squared, minus our final energy level, 1 divided by 3 squared. When we do that math, we find 1 over wavelength equals 9,760,000. And so I want to get wavelengths, not 1 divided by wavelength. So I take this 9 million, I do 1 divided by 9,760,000, and I see wavelength. My wavelength is equal to 1.02 times 10 to the minus 7th, or 102 nanometers, which again would put it in the UV region. All right, questions about Rydberg's equation? If not, we will move on to our next topic. All right, and this is the Bohr model of the atom. So Bohr took the work of Rydberg and all this emission and absorption spectra, and he created a model of how the atom looks. Now, let me just make a disclaimer. This is not real. The atom does not look like this, but the Bohr model of the atom is a good way to think about the atom. So conceptually, we can use it. And then we're going to learn later today and on Monday what the atom actually looks like. But what the Bohr model of the atom is that in the center, you have your nucleus. And around the nucleus, you have like these rings, right? Almost like the sun is our nucleus and the planets around the sun are our rings. Now in the Bohr atom, our Bohr model, electrons are in these rings. And the closer you are to the nucleus, the lower your energy is. So that's why we have energy level 1 being the closest, energy level 2, energy level 3, 4, and 5, so on and so forth. And what the Bohr model shows us is that to get to different energy levels, if I want to go from 3 to 4 example, I need some amount of energy. And then when I leave that level, I give that energy back in the form of light. And what's interesting, or not interesting, but something about the Bohr model and about emission in general. The bigger the gap, that is the gap between energy levels, the higher energy of light emitted. So what I mean by that, if we look at this electron that I just circled, it starts at energy level 5 and it goes to energy level 2. That's a big gap. And so it releases high energy violet light compared to the electron down here, which starts at energy level 3 and goes to energy level 2. That releases lower energy red light. Remember, the lower the wavelength, the higher the energy. So this is high energy light and low energy. So this model kind of explains why we get different colors of light. The bigger gap you have to cross, the more energy you need to cross that. And so you'll let off higher energy of light. The shorter gap you have to cross, the less energy you need to do that. And so you'll emit lower energies of light. All right. Questions about that idea or questions about the Bohr model of hydrogen or the Bohr model of atoms in general? Okay, so we have one more problem for this PowerPoint. And I have a poll for it. I simply want you to tell me for my 3 energy transitions here, remember N is energy level, are you going to see energy being absorbed? That is, are we going to absorb light? Or are you going to emit light? So I have a poll so we can all answer that to see where we're at. So take a minute to answer this. And this will be last question for test 2. I have to actually change up the test folders because I realized I put the stuff we're covering after that in the test 3 folder, but I'll change that after class. This is the last question for test 2. All right. So I'm gonna call the poll there because it looks like we have an almost even split for each answer. So it seems there's still some confusion on like what these energy levels are saying, what's emission, what's absorption. Right. So I'm gonna go back. I'm gonna redraw the Bohr model here. 1, 2, 3. I need a fourth one. All right. So energy level 1, 2, 3, 4. So that's roughly the Bohr atom, Bohr model of the hydrogen atom. So if I'm going from a high energy level like 3 all the way down to 1, that means I am losing energy. If you go from a high energy or big number to a small number, you lose energy. So that's the emission. So A is emission. If I'm going from a low number to a high number, so 2 to 4, I need to absorb energy to go to a higher energy level. And really the logic behind this is that the nucleus is positive, right? Electrons are negative. So electrons want to be by the nucleus because they're negatively charged. So if I'm pulling electrons away from the nucleus, they don't like that. You have to put in energy for that to happen. That energy comes from light. So you have to absorb light to pull an electron away from the nucleus. While, again, if we're at a higher energy level and we go down to a lower energy level, where we are becoming closer to the nucleus. Electrons like that. They like being closer. They are becoming lower energy. And so they need to get rid of the energy they just lost, and they get rid of it by emitting it as light. Right. Now that you saw that and you had a chance to actually test yourself on answering that question, any questions about anything we've talked about up to this point? All right. If not, we will go on to our next PowerPoint. Again, this, I will make the change official by changing the where it is in our folders. But just to reiterate, not on test 2. All right, sorry, 3. We're on test 3, not on test 3, which is Wednesday. So this won't be on test 3. All right. What we're going to learn is we're going to look at how atoms and electrons actually look. So we are going to talk about quantum mechanics now. So just a disclaimer, quantum mechanics is really confusing when you get into it. And the reason why quantum mechanics is so confusing is that in our day-to-day lives, we use what's called Newtonian mechanics. That is, if I drop something towards the ground, it will go towards the ground. Gravity will pull it down. That's Newtonian physics. If I push something, it will either move or it will not move. That's Newtonian physics. So like every action has an opposite but equal reaction, whatever. I forgot the exact wording of that. But quantum mechanics, that doesn't happen all the time. Quantum mechanics is mechanics for something that are so small that we can't even think about it. Like we can't imagine how small an electron is. But because these things are so small, they get to play by another set of rules that big objects can't. For example, electrons are so small, they teleport. right? They don't like move in a line. They're just at one area, and then they're in another area. That's called electron tunneling. They just appear, right? Another weird thing about quantum mechanics: if you measure a property of an electron, you change that property, right? Something changes only when we look at it. If we don't look at it and we don't know it, the property doesn't change. When we measure it, the property changes. That's why Schrodinger's cat is a thing, right? And in that the experiment is like, if I send a box to you with a cat in it, and the cat's going to die based on a quantum mechanics event, the cat is both dead and alive when you get that box, because they're both states. And it's only when you open the box and measure it that that state is determined. It's really, really weird property. But we're going to get in just to the baby steps of quantum mechanics and just determine where electrons are in an atom. And to determine where electrons are, this is all based on probability, right? We can't say for certain, oh, an electron is here in the atom. We can say, you know, there's a good chance that an electron is in this area of the atom. That's what we're going to look at. We're going to try and determine where we can find electrons. Unfortunately, I cannot move the slide up, but I can rewrite the equation, which let me do that. So the equation down here is E equals minus 2.18 times 10 to the minus 18 joules. And it says N equals 1, 2, 3, et cetera, et cetera, et cetera. All right. So what we're going to learn about are quantum numbers. And a quantum number or quantum numbers, so Q numbers, help us predict where an electron is in the atom. Right? So we have different quantum numbers. And the first one we're going to talk about is the principal quantum number, right? And the principal quantum number we call N. And N is basically its energy level, the same as what we are talking about. So the first thing we have to describe when trying to find where an atom is inside of where to find an electron in an atom is we have to describe the principal quantum number. What energy level are you at? And this N goes from 1 to basically infinity. And they're integers. So 1, 2, 3, 4, 5, 6, 7, 8. And the higher the value of N, the more the more energy in that orbital. And all of our energies are going to be negative. When we talk about energies for quantum numbers, we only care about negative energies. And basically, the more negative you are, the better. If you are a negative energy, that means you're happy. The more positive your energy, that's bad. If you have positive energy, you're not good. So unlike humans, negative energy is a great thing for electrons. And the idea is, as we move up in energy level, our energy becomes more and more positive until eventually energy equals 0. If our energy ever equals 0 as an electron, that means you escape the atom. You're no longer captured in the orbit of the proton. You are now an electron that is all by itself, right? And we can calculate the energy of an electron based on its principal quantum number. And that was the equation. that's shown here. So the energy of an electron in a principal quantum number is energy equals negative 2.18 times 10 to the minus 18 multiplied by 1 over n squared, right? So it has this set amount of energy, and this is the energy of an electron, right? Negative 2.18 times 10 to the minus 18 multiplied by 1 divided by whatever energy level you're at squared, right? So this is how we can tell what is the energy of an electron depending on its principal quantum number. And the next quantum number is shape, right? So after you figure out what is n, what's your principal quantum number, you can now start to determine what shape the orbital is in. So what is an orbital first? Let me define that. An orbital is an area of probability where you will find an electron. So an orbital is an area of probability that you'll find an electron. And our second quantum number, L, the angular momentum quantum number, it has integer values as well that range from 0 to n minus 1. So what that means is that if you're looking at an electron that has a principal quantum number, n, an energy level of 1, the only value of L it can ever have is 0. If it's at the second energy level, n equals 2, it can have two possible L values. It can have an L value of 0, or it can have an L value of 1. It can have both, right? If I'm at the second energy level as an electron, my L can either be 0 or it can be 1. Either or, can't be both. Now, what do these L values tell us? Again, they're areas of probability. So if you have a L value of 0, we call that the s orbital, and you are in a sphere around the nucleus, right? So let's say that you're an electron with n equals 1 and L equals 0. What that tells us as chemists is that somewhere in this sphere, we're going to find you if you're that electron. We don't know where in that sphere you are. We just know you're in there somewhere. That's what we're trying to determine. If you are L equals 1, we call that the p orbital, and you look like two balloons that are tied together, right? So if you are, for example, the other electron I mentioned, where n equals 2 and let's say L equals 1, you are somewhere in this balloon, or these balloons. We don't know where you are. You're just in there somewhere. L equals 2 are like is the d orbital, and it's like 4 balloons tied together. L equals 3, the f orbital, super complex. You can either be like 8 balloons, or you could be like 6 balloons, or you could be this weird thing, which I don't even know how to call it. So as you get to higher and higher quantum numbers, your shapes that you can be in become more and more complex. But basically, you're never going to have an L greater than 3. The f orbital is generally where you stop, unless you're like, there are elements that are bigger than that, but we're never going to talk about them. All right. So I know a lot of this stuff is probably confusing and doesn't make much sense because we're talking about, something 100% different than what we've been talking about all semester. But does anyone have like any questions that they can verbalize on what we've been talking about so far before we get to actual working problems? All right, if not, we will go on to our next slide. Yeah, the next quantum number we have is called m sub L, right? So this is our third quantum number. We had N, we had L, now we have m sub L. M sub L or ML, this is what orientation your orbital is in, right? And the value is minus L to L. So let's say that you were an electron that was in the second energy level. We found out your angular quantum number, L, was 1, which again we call the p orbital. Then you have 3 possible values of m sub L. This could be either -1, it could be 0, or it could be +1, right? Minus L to positive L, and you include 0. Like I said in the previous slide, you can only have one of these values. So you can either be -1, you could be 0, or you can be +1. What this tells us is orientation. And this is the easiest to look at for our p orbital, which is 2 balloons, right? So let's say, I'm not sure if these are right, but we have m sub L being -1, m sub L being 0, m sub L is +1. So let's say your m sub L is -1. What that means is that you're in the 2 balloons somewhere on the x-axis, right? So imagine that right here in the center is our nucleus. And on L equals 1, m sub L equals -1, we have our p orbital going across the x-axis. If m sub L is 0, our p orbital is now going across the y-axis. And so that's where you'll be found. If m sub L is +1, we have our orbitals going on the z-axis. That's where you're going to be found. So this m sub L is just telling us, if looking at our orbitals, more or less what direction or what orientation are they in? If we look at, and maybe it'll also be easy to understand if I talk about L is 0, which we call the s orbital, right? The s orbital is just a giant sphere around the nucleus. M sub L values are, L equals 0, my bad. M sub L values for L equals 0 is 0, right? It's plus or minus L. Plus or minus 0 is still 0. Because if I have a sphere, a perfect sphere, I can only have that one way. Like if I turn the sphere, it's still a sphere. If I flip the sphere upside down, it's still a sphere. Not true for the p orbital. I can turn this 90 degrees and get like that. Now they're different, right? So that's what m sub L's mean, 1, 0. While if I had a sphere, if I turn that 90 degrees, that's still a sphere. It looks no different other than my bad drawing. So that's what m sub L means. So we've had N, L, and m sub L. So let's start using them now. So I have 3 orbitals here. I want you to tell me, what are we looking at? Are we looking at S, P, or D? And I have a poll for this. So tell me, and I forgot. So shape 1, shape 2, and shape 3. That's how I name these in the poll. So tell me for these shapes, and I actually asked it a little bit differently. what is the quantum number we're looking at in these shapes? So that's what my poll is. And once you have that, try to determine to yourself, is this an S, P, D, or F orbital? Do about 30 more seconds. All right, so I'll end the poll there. So looks like the majority of us got it right. There's still some confusion there. So make sure you look over these. So if we're in the two balloons tied together, that is our L equals 1, which we call the p orbital. If we're a perfect sphere, this is L equals 0, which is the s orbital. If we're four balloons tied together, this is L equals to the d orbital. Not the orbital, the orbital. Right? So, and again, these just tell us where we can find electrons. If I'm an electron with L equals 1, I'm somewhere in that balloon. Questions about looking at our angular momentum quantum numbers? No, we will move on. All right. Let's see if we have this. If I'm n equals 4, what are all the possible values of of L and m sub L? So n equals 4, n equals 4, L equals what, m sub L equals what? See if you can use the logic of our last few slides and put this one together. And I think I'll make this the last question we do for today, as we are running short on time. And I'll just rewrite the rules in case you're still a little confused. Your L values go all the way from 0 to n minus 1. Your M sub L values go from plus L to minus L. Remember to count 0. And they are all integers. Right. So what I'm going to do is I'm just going to start and label all the L's we have, right? All of the possible values of L. So L goes from 0 to n minus 1. If n is 4, that means L goes all the way to 3, or could. So L, the possible L values we have, if we are in the 4th energy level, which is n equals 4, is that our L could be 0, which is the s orbital. Our L could be 1, which is the p orbital. L could be 2, which is the d orbital, or L could be 3, which is the f orbital. Right. Now that we have our L's, let's do m sub L, which range from plus L to minus L. So if L equals 0, the only possible value of m sub L is 0. If L equals 1, it could be 1, 0, or minus 1. If L equals 2, well, it could be 2, 1, 0, minus 1, minus 2. If L equals 3, it can be 3, 2, 1, 0, minus 1, minus 2, minus 3. And an electron at the 4th energy level will only have one combination. For example, so if I'm an electron, if my n equals 4, well, my L could be 2 and my m's of L could be minus 1. Only one, each electron only gets one set of these. And again, these are telling us where we can find an electron around our nucleus. But for all the possible values of L and m's of L, that's this. So the easy way to write this is L could be anywhere from 0 to 3. M's of L could be 3 to minus 3, depending on L. That's why I wrote it out like I did, because M's of L directly depends on L. All right. Any questions about our friendly swim through the world of quantum mechanics? Just dipping our toes into the water of quantum mechanics. If not, I'll put up a homework and I'll make sure that this PowerPoint isn't in the test 3 folder anymore. Again, as a reminder, in case you came in a little late, we will finish up this PowerPoint on Monday, and then we'll probably have like 20, 25 minutes for any review. If you have questions for me. If nobody has any questions they want to go over, then we'll just have a short class on Monday. So make sure that you review over the weekend and you look over all the PowerPoints, the previous test questions, and you have those ready to go for Monday. Otherwise, I'll put a homework up and I will see people on Monday. Have a happy Halloween, everybody. Take care.